Good afternoon and welcome to this worked exam answer video where today I am taking a look at a calculation question from the acids and bases topic of the AQA specification. And one of my students has been having a look at this and asked if I could do a worked answer for them. So I thought it would be great to do a worked exam answer both for them but also for all of you guys, because this is a particularly nasty question. So the reason why this is particularly nasty is because we're going to have to do something that we normally would not be doing for a weak acid calculation. And I'll explain how we know to do this for this particular question. You'll probably be pleased to hear this is the only one of its kind that they've used so far. But there is one clue in the question that suggests that this is not a normal weak acid, if you will. So the question says, I'll just zoom in a little bit. The question says that a solution that contains 605 milligrams of sodium hydrogen sulfate in 100 centimeters cubed of solution has a pH of 1.72. So that's quite a lot of important information already. We've got a mass, albeit in the wrong units, of sodium hydrogen sulfate. We have got a volume for the solution, and we know the pH of the solution. Our job is to calculate the value of Ka for the hydrogen sulfate ion, which is the HSO4- with the Na being Na+, and it's that ion that is behaving as a weak acid. Now, we already knew it was behaving as a weak acid because they've already mentioned that we're going to be calculating a value for Ka. Then it says give your answer to 3 significant figures. So that is going to be essential for the answer mark here. If you don't give it to 3 significant figures, you won't get that final mark. And we also have to state the units of Ka as well. So there's a couple of places you might wish to start here. I personally am going to start by writing a dissociation equation for the hydrogen sulfate ion, which is acting as my weak acid. So HSO4- will be dissociating into a H+ ion and then our sulfate ion, SO4 2-. Now I've got my reversible hour in there because it's a weak acid, so we only have slight dissociation, unlike a strong acid where we get full dissociation. And because we are dealing with a weak acid on its own, and we're not thinking about a buffer solution in any way, for every one HSO4- ion that dissociates, we generate the H+ and the SO4 2- in a 1-to-1 ratio. So what I would always do is encourage you to write your Ka expression in full first. So we've got the concentration of the 2 product ions on the top of my fraction, and then we've got the concentration of the hydrogen sulfate ion, a weak acid, that goes on the bottom. And I would always encourage you to write it like that first. But for weak acid calculations, we can say that because we make the H+ and SO4 2- ions in this example in a 1-to-1 ratio for every HSO4- that dissociates, we can then simplify that to say that Ka is equal to H+ squared divided by HSO4-. Now, normally what you would then do in a lot of questions is rearrange that Ka expression to get H+ equals so that we can then get pH. Now, we've already got the pH of the solution, so we're not wanting to rearrange to get H+, because we're wanting to work out Ka. We've already got it in the format that we need. So now we just need to figure out H+, and then we can figure out the HSO4- concentration as well. So that's all going to come from that top line there. So Because the NaHSO4 in solution is giving us this HSO4 minus ion, if we work out the concentration of the NaHSO4, that will be the same as the concentration of the HSO4 minus. So that's going to help us to get the concentration of this on the bottom. The pH is going to be used to get the concentration of H+, which we can then square on the top. So, doesn't matter which order we do this in. I'll do the pH bit next. So the concentration of H+ can be worked out from pH by doing 10 to the power of minus pH. And on your calculator, that 10 to the power of, then you can put minus whatever the pH is the same button as the log button that you would use to work out pH from H+. So that's quite handy. So on my calculator, I need to do 10 to the power of minus 1.72, which gives me 0.0191 moles per decimeter cubed, and I've written that down to 3 significant figures. That's what we're aiming for overall at the end, so I'm going to stick with my 3 significant figures from here. So that's the H+, and that can go in the top of our expression and be squared. Now we need to do some work to get the HSO4 minus concentration on the bottom. So the first thing I need to do is put my milligrams for my mass into grams. So we do that by dividing by 1,000. So we're going to have 0.605 grams. And I'm then going to need to work out the MR of NaHSO4, which is 23 for sodium, 1 for hydrogen, 32.1 for sulfur, and then 4 lots of 16 for oxygen, and that gives me an MR of 120.1. Then with those two values I can work out the moles. So moles is equal to mass divided by MR, so 0.605 divided by 120.1, which gives me 5.04 times 10 to the minus 3 moles, and again that is to 3 significant figures. And then we've got a volume which we need to convert into decimeters cubed, but once I've done that I can then use the moles and the volume to get the concentration. So the concentration of the NaHSO4, which is equal to the concentration of the HSO4 minus ions, is equal to moles divided by the volume. Volume should be in decimeters cubed, so that's going to be 0.1 decimeters cubed. We go from centimeters to decimeters by dividing by 1,000. And if I take my moles and divide it by 0.1, we get a concentration of 0.0504 moles per decimeter cubed. Now, in every weak acid calculation that you've probably seen up until this point, you would then, if this was the nature of the question, working out a value for the Ka constant for a particular weak acid, you would sub in the H+ concentration and square it, and then you would just sub in the concentration of the weak acid into the bottom part of our fraction. Now, if you were to do this on this question, you would still be able to get 5 of the 6 marks. So if what I'm about to explain confuses more, or you just think I wouldn't know whether I should be doing that or not, please don't panic, because you will still get all but 1 mark for doing it the normal way. The reason why we don't do this the normal way comes back to the value for pH. Now, if we think about pH values that we've been calculating in the acids and bases topic, a pH of 1.72 would be something you'd be more expecting to get for a strong acid pH. You don't often see, or don't ever see really, weak acids that have a pH that is that acidic. I would say if it was 2.72, okay, I'd probably be okay with that, but because it's all the way up at 1.72, that the first time I ever read this question rang alarm bells of, oh, that weak acid has quite a big or quite a strong acidic pH. Now, the assumption that we make when we normally do weak acid calculations is that whatever the concentration of the HSO4 minus in this instance, or whatever the concentration of your weak acid is initially, we just sub in that number into our Ka expression or our rearranged Ka expression, because the amount of dissociation is so slight that the amount of HSO4 minus that dissociates, or whatever the weak acid is in a normal instance, would be minimal. So the change to the initial concentration would be really, really small. So to make life a little bit easier for us, we just say, well, we're going to assume that this stays essentially the same, even after dissociation. So we've worked out, or we get told what the concentration is, and that's the concentration we sub in. That's the bit that we have to do differently here, because it's such a strong, in inverted commas, weak acid that we have to have quite a lot of this HSO4 minus dissociating. The concentration of H plus is quite big to give us a pH of 1.72, and therefore it would be wrong of us to not change the concentration of the HSO4 minus, because it is going to drastically change in this example, because we've got way more dissociation than we normally would have for a weak acid. So what we need to do for the value that we're going to put in the bottom here is we need to take our initial concentration of 0.0504 and take away what we know has been lost via the concentration of H plus that's been formed. So take away the 0.0191. That will then give us the concentration that we will be using for our weak acid in this example. And that is the bit that we don't normally do. And that is the bit that is going to get you the 6th mark in this question. Just to go over why we're doing that again. This pH, very, very acidic, far more representative of a strong acid than a weak acid, but we know it's a weak acid because we're told it's behaving like a weak acid, and we're calculating a value for Ka. Now, your value for Ka tells you the amount of dissociation. The value for Ka is going to be quite big here compared to a lot of other weak acids, because it has to be. We have to be getting quite a lot of dissociation to get a H plus concentration that is capable of giving us a pH of 1.72. And that is the only trigger point of this question, if you will, that enables us to know that that's a step we have to do. We cannot assume that the concentration of weak acid does not change once dissociation has happened, because there's so much dissociation in this case that it is going to change quite significantly. So the concentration's gone from 0.0504 down to 0.0313. That's a substantial change. So that's the value we're going to put in the bottom of our Ka expression. We're going to put the H plus concentration and square that on the top of our fraction, and that will give us our value for Ka. So Ka is equal to 0.0191 squared divided by 0.0313, and that gets me an answer for Ka of 0.0117. Again, remembering about our 3 significant figures, so I get 0.011655. So I'm going to round that to 0.0117. And that might not mean very much to us because we're so used to seeing Ka values as standard form. So if we were to write it as standard form, it would be 1.17 times 10 to the minus 2. And you can give either as your answer on the line, it doesn't matter, because they're both exactly the same thing. I've still used 2 significant figures, but if we were to think about Ka values that we use regularly, we'd be thinking about it being 10 to the minus 4 or minus 5, whereas here it's only times 10 to the minus 2. So a much bigger value for Ka because we've got a lot more dissociation of our weak acid here. So either of those values would be fine. In terms of the units, we've got two lots of concentration on the top, because we've got a concentration of the H plus and the SO4 2 minus that we simplified to H plus squared. So it'd be mole per decimeter cubed twice on the top, with 1 lot of moles per decimeter cubed on the bottom. So 1 from top and bottom will cancel, leaving us with units of mole per decimeter cubed. So what I would do here is exactly what I would be doing with my units for KC or KP, which is just subbing in the units into my, in this case, KA or my KC or my KP expression, so that I can then have a look at what will cancel. So 1 mole dm minus 3 on the top will cancel out the 1 on the bottom, leaving us with mole dm minus 3 as our units for Ka. I'm going to stick with my original 0.0117 for my answer, but like I said, either that or in standard form, so long as it's 3 significant figures, would be absolutely fine. So that is an odd one, and I understand the very small piece of information that was needed to know that we had to change the concentration of the weak acid in this question. However, as I said right at the beginning, if you didn't do that and you just did your normal Ka expression, then you would still get 5 out of 6 marks here. So please do not panic if you are now thinking, oh my god, how do I know when a weak acid is strong enough of a weak acid to do this? There isn't really a cut-off as such, but yeah, if we think about past paper questions that we might have done to this point, or when you do more past paper questions, you will see that the pH of weak acids normally is sort of 2.7, 2.8, 2.9, maybe even 3. So this is substantially more acidic than that. Hopefully as a method that sounds okay. As always, any questions guys, please just let me know, leaving a comment on the video or get in touch via email if that's preferable. Thanks so much for watching.